welcome everyone to this session on integrating OpenET into decision support tools. And my name is Lee Johnson. I'm with the California State University, Monterey Bay, and NASA Ames, part of the OpenET technical team. And first up, we have Olivier Jerphagnon. Close. Olivier is a serial entrepreneur with a talent for bringing new technology to market. He grew up around farms in Brittany, France, and is an expert in applying data mining techniques to solve practical infrastructure problems. He's a founder of AgMonitor Inc.'s data mining platform for addressing climate risks at the nexus of food, energy, and water. Prior to that, he had quite a bit of additional private industry experience. He holds 8 patents and has been published in more than 30 peer-reviewed journal articles. Holds an MS from UC Santa Barbara, go Gauchos. I was my Gaucho myself. And an engineering diploma from the Grenoble Institute of Technology in France.
Thank you.
Welcome.
I'm all good. Thank you so much. So this presentation is done in partnership with Terra Nova Ranch. It's one of the farms that pioneer in-situ groundwater recharge. So, as you move away from flood irrigation to drip irrigation, there are some infrastructure on farm where you can actually flood a field and potentially do recharge. So just want to acknowledge the collaboration of Terra Nova. My background is more data mining, and so what I'll talk about today is the integration of the open data on the energy side, which is the pumping data, and OpenET to help people create a long-term water budget and identify how much groundwater they need to bank to be able to maintain the water table. So there's a lot of data sets I'm going to incorporate today. If I go too fast, just raise your hand and ask questions. Feel free to interrupt me. We started this project funded by the Energy Commission in 2017. A lot of UC collaborators. Back then, we were just doing energy efficiency for utilities funded by CPUC. We grew from 25,000 acres to 250,000 acres under management. We also were instrumental in auditing the SWEEP program for CDFA. So they got refinanced in 2020 by the legislature. We're a big fan of open data. On the water supply, we have access since 2013 to all the meters in California through the Smart Meter program, and Texas and other states have that data available. And so when we saw OpenET emerge, we were very excited to kind of merge that crop water demand, which is one piece of the water puzzle, and the supply side. So if we merge those two data, there are many things you can do today. Water budgeting, looking at the impact of deficit irrigation. What I'll talk about today is a more exciting project, given the wet years we've had recently, is the impact of groundwater recharge on the water table. Just a little bit of background on the meter data. You used to have someone coming to your meter and take a picture, and that's how the bill was generated. Now, the 15-minute data is accessible to the utilities, and through the green button standard from the White House office and the DOE, a farmer can share its energy. And so through that, you can actually see all the irrigation events, and that's really good background information on farming practices. In our case, we actually did an AI algorithm to do a regression by integrating the pump test energy efficiency program. So through a 3-pump pump test, we recreate the pump curve and our water management method is accepted in California. It's about 3% error with a max under 10%, which is the requirement for the California Code regulations. For us, the key benefit of OpenET is to create site-specific KC. Why? Because it's great to look at the past, but what a grower really needs is a forecast. So, if you have rain forecast and you have historical average rate of T0 and microclimates, you just want to take what you learned from the past to create site-specific KC. And back in the day, sometimes it would take 10 years to get a UC funded project to look at what's the pistachio KC now. People do drip irrigation. So if you don't want to wait 10 years for the next publication and you want to know what is your KC for lemons in Coachella, for example, which is not very well covered by the publication, now you can have your own KC table. So we love that. So that's what I show on the left. On the right, what we hear from our growers is a translation. So inches and KC is great for the agronomists, but at the end of the day, the person on the ground, they just want to know how many hours they need to turn on the pumps. So what you see on the right is that kind of calendar schedule type of approach. The OpenET is in the ag hour column, which is kind of a agronomic reference, and then they decide exactly how they want to apply that water day by day. So here's an example of a lemons packer and grower that one of our customers asked us to work on, and in blue is the KC table from UC Cooperative Extension. We look at their yield data and their water data, and what you see in orange is the upper quartile. So that's actually, those are well-performing orchards. And the lower quartile in gray are the ones that were overstressed, and you can see the big drop in KC in the summer. And so now, you can actually use that to say, I'm going to adjust the blue KC a little bit. And so merging the blue and orange curve is basically the KC table that they're using. And we use the OpenET data to give them a few fields to look at. And 90% of the time, it's pressure issues. The design system is not well done. The pump is not sized properly. And that's why they have very uneven irrigation. So that's the background. Now I'm going to talk about how we integrate the OpenET data. We're very careful about it. So we do a data check every year when there's a release. We do full corner tests to understand whether the data has changed or not, and we pick one algorithm. We work with the extension system. We don't change the crop model. We use the FAO 56 or whatever is published. But when we have a site-specific issue, like the irrigation system, or like here, the Coachella Valley, we'll create a site-specific curve. So that's the second step. And then the third step is we create a forecast. How much water you're going to use this year or the next 5 years. So today I'm going to talk about Don Cameron, who pioneered groundwater recharge. He thinks in acre feet. But for us to be used by the team, I also want to let you know that for adoption, you need to have an hour calendar schedule for the ranch manager. He doesn't care about acre feet or inches. And the agronomist that does the fertilizer or the chemical prescription, he really thinks in the root zone. So if you really want to be used as a tool, you have to do all those three things for those three type of users. Today, I'm just going to talk about the blue one, which is the person that buys or water or works with the district to bank the water. Full corner test. We have a few vineyards or a few ranches where someone made a mistake 5 years ago and the ET crashed. So we check how fast the ETA data is going to find out that it's actually not good. Spatial sensitivity, we're very careful about the shape of the shapefile. We found that below 10 acres, the size of the shapefile starts to create errors. So we try to work with properties bigger than 10 acres. Crop accuracy, there were a couple of crops that were not measured very well 5 years ago. Citrus was the one because of the shiny leaves that were overestimated. So some of the GSAs were not happy. So citrus is something we check all the time. That's the one that usually fails. And then we have a crop diversity, like Terra Nova, 16 crops, mix of row crops and tree crops. We try to see, if the algorithm is going to give a reasonable answers across all those crops. So here's an example of temporal tests. We test that every year. In 2018, a field was severely underirrigated, plus another chemical issue happened, and the ET just collapsed. For 2 months, there was almost no transpiration. What you see in blue is a SIMS ET measurement. The dark red dots are the flight dates. And when you look at the ensemble ET, some people say it's more accurate this morning, especially true, but because it's an average, it takes longer for that ensemble to figure out that that field actually not transpiring. So in this case, SIMS is really the winner for us. Ensemble, although it's more accurate, doesn't really give us a weekly response when there's a farming problem. Here is the test we do at Terra Nova. We measure with flow meters and smart meters multiple years of groundwater truth. So it's accurate plus or minus 2%. You know, we're paid by the Energy Commission to have a few test beds. The red data is the same algorithm as of today, which is just the 21 release. You can see that Ensemble was the most accurate. You know, it was almost right on the dot. And you see a little bit of variation across algorithms. We run the same tests with the recent release for the 24 models. And overall, it doesn't change much, but you can see there's some variations. And so for us, when you combine good spatial and crop diversity in terms of resiliency and the temporal response, we end up choosing SIMS for our application. But again, we love OpenET because when you start a project, you have no idea what you're doing. And so it took us years to figure out what the grower wanted. We select some tests, and then we can pick the best crop for, the best model for us, but maybe another application will use another one. So we love the collaboration. So for us, we're gonna use the crop demand, I'm starting from the right, to generate a water load. And then that water load is gonna create an energy and cost load. The state, as you know, is trying to integrate more renewable energy, and so there's price signals like penalties from irrigating between 5 and 8 p.m. And so the farmers are dealt with this conundrum is, how do I react to price signals on the left moving to right? And how do farming from right to left? And so the person who turned the pump on and off has all the problems because he's right in the middle. So in the case of Don, he tried in 2019 a pilot program for on charge. In situ groundwater recharge, it worked pretty well. You know, they had some probes, 90% efficiency. So he got $10 million to build some canals and put that huge pump, 150 CFS. So it's, you know, 5 times bigger than a person. Usually, you wouldn't be able to see the impact of a farmer on a groundwater table because, you know, the basin is very large. In this case, it works because at the bottom of the basin, so the water stays there. Otherwise, I could not present the results today. It would just be washed across, you know, 100,000 acres. But here at the bottom, so whatever they put back, it actually elevates the water table. So as I mentioned, we can do forecasts. So the purple line here, based on the historical ET data, we have KC tables. We use the average 5-year ET0. And we know within a few percent how much water they're going to use. Now, in 21 was an average year. It was pretty much exactly the same curve. In 22, it was a big drought. So you can see the blue line, they put more water beginning of the year because they were recharging the soil profile. You know, rain was not there, so you have to put that in the soil. And then in the summer, they did deficit irrigation, and they kind of ran out of capacity. And so you see they start to do heavy deficit, and, you know, they were able to survive. So 22 is kind of the interesting curve. The reason we can measure everything is we have a mixture of methods. So everything works. So for some sites, you know, there were 3 outputs from the well. Impossible to put a flow meter, you know, it would cost $30,000 of repiping to do a flow measurement. So we just do the smart meter at 3-point pump test, works really well. In some other cases, you have 2 pumps on the same meter, so you cannot use the energy meter. The flow meter works really well. So using those 2 methods, we have 100% data coverage across 30 pumps and 9,000 acres. So that's we know how much water is being pumped for extraction. In 2023, as you know, we had a lot of rains. Don Cameron, which is the president of CDFA, worked with Karen Ross and the Office of Governor Newsom to try to get some permits to do groundwater recharge. So Terra Nova is along the Kings River, and there's a liability. So at some point, if people cannot use the water, it will actually flood the city of Mendota. So based on the flood risk, they got a permit to divert water in March 2023. So on the left side, you have this letter from a district. They had an engineer measuring the diversion, and it was about 77,000 gallons per minute, so about 150 CFS. The district tried to put a permanent flow meter, but the amount of water is so huge, it got buried under mud within 2 weeks. So the district didn't have any water data. And Dunn was a little bit upset because, that's a credit for him. He's going to work with the GSA. So what we had was the hours of the pump that was taking water from the diversion canal into the canals feeding all those small pumps. And DWR had this lending program, so you could put some loaners and you just flood those fields. So we actually used the runtime method times that certified flow measurement from the district as an approved State Water Board measure. And Don was able to send the data to the State Water Board, and he's working with GSA to get that credit. We were targeting over 18,000 acre feet, and he was able to pump 19,000 acre feet. And here's why. He used about 3 acre feet per acre. We found over the last few years with deficit irrigation on almonds, sub-drip irrigation for tomatoes, actually only using 2.7, so ETA is very useful. We also saw that on the pumps. The GSA safe yield, which is the curtailment is going to happen in the next 2 years, is 1.7. So Don is to figure out how he's going to save 1 acre feet. Point 2 is going to come from following some fields. It's going to put solar for 30 years with a project developer, so that's about point 2. So he needs to recharge about 0.8 acre feet. Let's say we have a flood every 4 years. 3 years of drought needs to be compensated by 1 recharge. So we came up with the estimate of 16,800 acre feet coming in. We knew that to have an impact on the water table, you need to put at least 17,000 acre feet. That was really helpful for Don because he was really battling the permitting with the county and the state to start recharge in March as opposed to May, because you only have 4 or 5 months before you kill the crop, and you have to stop first week of July. You cannot go too far in the harvest season. So this is my contribution today. This is the impact on the water table. This is real. We have had a depth sensor for 7 years. You can see in July 2019, it's about 20 acre feet, and we had 3 years of drought. July 2020, we lose about 10 feet. July 21, another 5 feet, and 22 at the bottom, it's more than 20 feet. Coming into 23, things come back up through winter, that's normal. And what was really surprising when people start to turn on the pumps in June, July, August, the seasonal drop did not happen. It kept going up. So that was just incredible. We shared that with DWR. They were very interested. They looked at diversion point data, our data, but really this is what confirmed that it was working. Now DWR said, well, I'm not convinced. Let's see the answer in winter, because you have to measure things in summer and winter. And sure enough, in the winter, we're back to where we were in January 2020. So in 6 months, they erased 3 years of drought by banking 18,000 acre feet. So that data is, that's the validation. Everything else is really planning. And again, contribution of deficit irrigation, recharge, all the things really matter. And OpenET is a very valuable tool. So my takeaway is OpenET allows us to provide site-specific KC, which is really important for planning and budgeting. We measure groundwater extraction, and so recharge using the energy signature of all those pumps. Terra Nevada met their goal. They erased 20 feet drop in 6 months. I do believe, some people compare measurements. I think all the tools we have is really complementary. So my takeaway, supply and demand is one way of looking at that pump and satellite data. So we think it's very complementary. And then for research collaboration, where we're starting to work on is data fusion of different data layers. So anybody working on that, we're interested to work with you or talk to you separately. Thank you for your attention.
Thank you so much, Olivier. Appreciate that. We have time for a quick question, if anybody's.
What was the cost of the groundwater recharge per acre foot?
The question is, what is the cost of the groundwater recharge per acre foot?
If you put aside the infrastructure to put the canals on the grant, which is, you know, a very high cost, the cost to lift the water was only $7 per acre foot. Now, as the GSA expands that 50,000 acre pilot, the Macmillan GSA is going to finance something much bigger. I would imagine that, you know, the infrastructure cost amortized over 30 years would be the largest expense.
So the reported cost of energy was $2 million something dollars?
So that's the groundwater extraction. The piece for recharge was like $100,000.
Oh, okay.
Because, you know, that's only one pump out of 30. I should probably not put that dollars, but Don didn't mind.
I saw the dollars in energy and the dollars, and the amount of groundwater banked, and that turns out to be $140.
$100,000 there. Now, the reason why we're financed by the Energy Commission is this drop of 20 feet means your efficiency goes down by 10–20%. So the fact he was recharging is probably saving about $500,000 a year in pumping costs. So that's why we're financed by the Energy Commission.
Thanks so much.